Hello, everyone. Welcome to the 7th session of PADL. And we are going to start with Dr. Fang Li, ASP for Provenance graph-based cyber threat detection.
Hi, everyone. So actually, the name, this is a truncated name. So because the name is so long, so I just make it shorter, put it here. So basically, the idea of this research is it's a concept proof, a proof of concept that we are able to apply the ASP to the graph-based some reasoning, especially, for example, in this case for cybersecurity threat detection. So let me tell a little bit about the background of this research. So the thing is, we got the motivation. Says why is this research? But the actual motivation, one layer above this motivation was during my teaching. So I was teaching intelligence system class, and during the class I was trying to promote declarative programming, right? So and also the department wanted me to teach another course, which is guiding graduate student to do some research, right? Which we're a teaching school, which is very rare. But I was trying to show my student how to write a research paper, start from scratch. Then I started showing them, hey, you need to figure out a topic and try to do the literature research to see is there any similar stuff, and then keep doing, come up with your idea, and then do implementation, write the paper. So before the semester ends, before they even submit their homework, I finished my paper. So, then I know the PADL is the one, it's like in November or something. It's like it's perfect time I submitted the paper. So this is the original motivation. So then the actual motivation here academically is that I was also told that because we have a lot of colleagues working on cybersecurity, so there are a lot of things you need to do. They're very, very hard to find those patterns and to detect the threats or something. It rely on human expertise, some experience stuff. I said, okay, my professor, my advisor, Dr. Gupta, told me that this is the perfect place to apply ASP, right? So I was thinking maybe we are able to do ASP to handle some of those cybersecurity problems, right? So then I contact the second author, which is another professor at another university. He's working on cybersecurity. I talked to him, hey, is there any scenario in cybersecurity could be represented into a directed graph, right? He was thinking, hey, so he said there's a thing called provenance graph. So that thing is able to, provenance graph is what they use to sort of replace the system log, right? So I'm not a professional on cybersecurity, but he told me about this. So they use the graph, the nodes, and the edges to link the entities. For example, you got a user. The user opens a file, right? So the user is a node, file is a node. Then the edge means opens, also with some time step or something, right? And then some process visit internet request, right? Then visit somewhere. So you also link those two entities together using some edge, right? And with some properties for the edge, like time step or some whatever, the privilege or something linked. So they put the whole thing as a graph. I look at this as it's very familiar to me, right? So you got components, you got a process, files, connections, which are the nodes. You got edge, you got a read, write, fork for execution or something, and also got temporal information and metadata. So it's very easy for us to model, right? So I said I'm able to find a way, a different way. Maybe nobody ever done this before to help you guys do some reasoning on those provenance graph, right? So before we did some literature research. So how people deal with the provenance graph? They use some, they search in the graph. They use some Neo4j, like those kind of implementation stuff, the database. They try to do something, right? So they can do like policy compliance, the forensic, computer forensics or something, and attack reconstruction. Try to identify to redone the attack, how it happens. And also the limitation is the queries are very complicated. You are searching on a very large graph, huge graph, right? So, and also the reasoning, they cannot do too much about the reasoning as what we call the reasoning, right? As declarative people here. So I think, okay, maybe we can apply the ASP. So, but why ASP? So ASP, the first thing is declarative, right? Declarative means that programming without how, right? You just tell the computer what do you have, what do you want. That's it. Computer will figure it for you. This is called AI, right? Artificial intelligence. Not like you need to give the computer step by step, like a C++, Python, right? You need to do this. Without your instruction, the computer cannot do anything, right? That's not AI, that's artificial idiot, right? Sometimes I call it, right? So the thing is, we do this declarative as a good pro, and then based on stable model semantics, right? So, and also it supports non-monotonic reasoning. This is the most important part, I think, because for cybersecurity, a lot of knowledge, a lot of patterns, the rules you define, sometimes the later rules might conflict with the previous defined rules, right? What can you do with that? With monotonic reasoning, like a prologue, so you have to explicitly define everything, right? So, for example, bird can fly. You say like if X is bird, then X can fly. But later you meet penguin. That won't work, right? But for ASP, like non-monotonic reasoning, you have default reasoning. Negation as failure. You define the bird. If it's not abnormal, then the bird can fly. So later, no matter what kind of bird, weird bird you meet, you just label that guy as abnormal. That's okay, right? So this thing is a big plus for reasoning in this kind of task. So so I still have to introduce some ASP, right? So this is the basic syntax. So you got the head, the bodies, right? So you got the positive atoms and also some negative ones. This is negation as a failure. So the not, the NOT with some term is not the same as the classic negation not. The classic not, for example, is you say not P. That means you have proof that P is false, right? But with this kind of not, that means you don't have proof that this guy is true. That's the biggest difference, right? So this is the rule. And also, of course, I omitted some part. So we got the constraints, like the headless constraint, right? If you remove this head, this means what? This means these three guys cannot happen together. If they happen together, you got nothing, right? So that means that's a constraint. Also, we have like a P if Q, comma, not P. This is another way to define the constraint, right? So this is ASP. And why we need to combine those? How can we combine those together? So since we already got the provenance graph, right, which is pretty much like causal relationship, you got this node pointing to this node. We are able to model them use ASP, right? So the targeting node is the head, right? So the starting node is the body. That's it. And then also we can define the whole thing, right? So encode the whole provenance graph into the ASP format. So for example, we got the basic representation. We got nodes, we got a process, right? You got the files, you got network, etc. You can have more. Because, by the way, I need to mention that in the cybersecurity community, there's no universal defined provenance graph format yet. So that means it's also a big plus for us. We are open to customize, right? So in this case, the edges, you get from node to another node, the type, right? For example, you process access the file. So the type is going to be access, right? Then T is the time step. So this is the basic, one of the basic one. And here are some core ASP rules. Like one of the ones is reachability, right? So the reachable, this rules define the reachable. So from this node and that node, I mean, can you reach this node from that node through in the graph, right? This is reachability. Then temporal ordering, you need to define which one is earlier, which one is later, because temporal, right? So for the system. Then causal dependency. So it defines these two are, this one is depending on some other nodes. We also need to define this kind of stuff. So this is the basic stuff. And also we have some advanced rules for like attack path tracing. So how you got a process, right? You got reachable. Then you know this one caused some attack. Then you can trace back to find, hey, which guy started this one, right? Or which processes is possibly be affected by this attack, right? So we are able to trace back. And data exfiltration, that means you want to you define the connection, the process, and the file. So the process did something to the file and send some data somewhere else. So this might cause problem, right? So again, I'm not an expert on cybersecurity. Those are my co-author. We discussed with each other. He gave us a lot of this kind of information, right? Again, this paper is a proof of concept. So we just want to bring the possibility. This is the way we can apply, right? So this, this might not be 100% true, right? So, but this is just an example. And also we got the root cause analysis. You want to dig back to see what is the actual cause, the original one, the troublemaker, right? And also for the alert generation, so this is just like some information, a message passing or something. It tell you, for example, unauthorized access to a sensitive file, right? If you got a file is sensitive, somebody visiting this might be a threat, might be not, right? We don't know, but we need to let the user be aware of this, right? So this is one of the things. Now, the capability, so we are able to comprehensive attack path analysis do this, and we are able to detect data exfiltration attempts, and root cause and automated alert generation. Those are based on those rules that we defined before. So the benefits is it's flexible and extensible, right? What is extensible? Because our non-monotonic nature, right? Non-monotonic nature. So, and every user is able to define their own threat pattern, right? Anomaly pattern. So clear expression of security patterns. So with the structure, right? Like ASP rule is pretty much easier for us to understand, right? So, and also integration of temporal reasoning, we got a time step, right? And also support for complex attack scenarios. So it depends on how well you design your pattern, right? The pattern, right? The rules. So like this is example, like a little bit more complicated than advanced rules here. This is a multi-stage attack detection. So based on the compromise, based on the data exfiltration, and based on some of the privilege escalation, we say if anything meets this requirement, it's probably going to be a multi-stage attack, right? So we're able to apply this to help the security people to be alert, right? Like this. And also the detection rules, we're able to detect the privilege escalation by using, if you got a process, previous it has low privilege, and later this guy raised to higher privilege. So this escalation, you need to be aware of this kind of a scenario also, right? So, and the thing is, the implementation part, we use SCASP system, because SCASP is a goal-driven, right? It's goal-driven. So because like a Provenance graph could be very big, very large. So if sometimes we just wanted to, for example, the security engineer, they are not sure about some small portion, he can just make a query on that related nodes, right? So you got a pretty decent result of this part. So we try to use Klingo, but it's way slower than SCASP. So we use SCASP. So the challenges, again, through my entire academic life, scalability is always the nightmare. So this one also being, dropped by scalability, right? If you got a very large graph, very complicated scenario, right? Entanglement, right? So it's hard to handle. So far, and the state space explosion at the same time, and the real-time analysis is a problem right now. So far, but just like the survival game, right? You are sort of can do some real time, but it's in the current stage we haven't do anything with that yet. Knowledge engineering, right? This is a very hard knowledge engineering. We need to who defines those rules, right? Who defines those patterns? That's the problem, right? So we need some input. But again, this just want to bring a method to above the table to let everybody see, hey, we were able to do this, right? Our future goal is, I have a little bit ambitious goal in the future. So I want to build a platform not just like a application, a platform, and also with a DSL, a domain-specific language, provided for the cybersecurity people, so that everybody is able to submit, upload their own pattern, threat pattern, anomaly pattern, whatever, right? So the user able to download those, right? Like add-on or whatever thing. So whenever, if you got some, your dot, you got some system log, so you don't know whether your system log, somebody intruded your system, you can upload that log file to the online system, and then you choose the possible attack or something, then you do a scanning, right? So this is going to be my future goal. But currently, we still have a lot of work to do. This is just like a starting point for this research. Thank you so much. Yeah.
Questions? So I'm assuming that the detection rules, you wrote them together with a cybersecurity expert. How long did it take to come up with those rules?
The rules is, we wrote the paper pretty quickly.
Uh-huh.
Finishing the paper within 1 week. So, but the idea through the whole semester,
Uh-huh.
discussing with the guy, he was writing a lot of complicated rules. But to me, those are not so applicable. I simplified those. So like the file exfiltration, like those multi-stage. So it's supposed to be very long, but I don't think it's a good idea to start with those. I said, okay, can you minimize, just like Elon Musk asking his engineers, can you minimize, simplify those things? So the guy just gave me, okay, those you cannot be less than those rules. That's it. That's the bottom line. So I said, okay, I will put the bottom line as our case. So this, some of those rules are come from this way. Yeah.
One more question.
Yeah.
On the last slide, you mentioned machine learning integration.
Yep.
What are your ideas with that for the future?
That's a good question. So because we rely on knowledge engineering, we want to define those patterns stuff. So my plan is to use large language model or something, and then to generate, help us to generate the patterns, the anomaly or threat, those kind of the rules. And also, not directly do that. We want to generate some synthetic scenario and try to analyze those. And then, so here I mean using machine learning is pretty much this way, not on the reasoning, just on the defining. And yeah, thank you.
Other questions?
I think it's not the first time that I make this comment, but. Don't you think that probabilities could have the expressive power of this formalism? I mean, in order to formalize the model or the problem that you have. Well, I started using logic rules with probabilities at some time ago, and now I think that they are always needed in the sense that it's almost impossible that you have a domain where the rules are always deterministic, always clear. Typically, there is some probability involved. So I wonder if this is the case here. Whether can you could improve the model using probabilities too.
Before I answer this question, let me just talk about my current change in my belief of research. So I've been with Dr. Gupta all the time, right? So for my PhD, so we are a believer of explainable AI. I believe most people here believe this. But these years during teaching, I started to realize that probability, non-deterministic uncertainty is more important because we define artificial intelligence. We are not even able to formally define what intelligence is. How could it be possible for us to make artificial version of it, right? So we need to admit we are limited. So we need to admit some of the system. We're able to build a system which we couldn't fully understand, right? So this being proved to be true, right? Look at this wave of AI, right? So like the chat robot, well, Dr. Gupta was leading us as a team. So Sopam might know that we participated in Amazon's Alexa competition. before I graduated, 2021, believe we were the 9th team over the 500 teams worldwide. And we were the only team didn't use machine learning. We use rule-based. And so the competition is you build a chat robot. They got a lot of people to chat with the chat robot and to see who lasts longer, which team lasts longer, right? So, but nowadays nobody wants to hold this kind of competition because it's ridiculous. Right now, ChatGPT, every those kind of large language model can chat with people for a long time, right? So why it succeed, and also the application of the hidden Markov model on the speech recognition or whatever things, right? So they applied probability, they accept uncertainty, they admit that we human cannot fully understand this world. So how about we accept the explainability, right? Here is very good question, sir. So for our system, the same thing. Eventually, I want import probability into all of my researches. All of my research, more or less, maybe different level, but I need to handle the probabilities. For here, you see, I noticed there's some ASP approach has non-deterministic, right? Has a probability integrated temptation right now. So next stage, I'm also will look at those kind of papers to see whether we're able to do some integrate the probabilistic reasoning into our platform. So the other thing is, for now, I was told that like in cybersecurity, there's no like a universal, like a formalized definition of those attacking or something. So so that's why we're open to customize. So everybody is able to submit their pattern or something, right? So because we're not monotonic, so this should be okay. The whole platform should be able to handle the thing, right? Thank you.